Right. So good afternoon, good afternoon to those of us in Europe and Africa. Good evening to those of us in India, and good morning to those in America. Uh, it's just about time to start now. So just let me, which everybody seems to be doing. So uh, while while you're not talking, please keep your microphone muted to avoid any unnecessary background noise. And I'd just like to say for the speakers, after you've been speaking for 17 minutes, I'll interrupt you just to say that, well, your time's nearly up. The talks, including questions, are 20 minutes. So please keep an eye on the time. And then our first speaker is Kustav Chandra, who'll be talking about an optimized PYB search for gravitational waves from intermediate mass black hole mergers. Okay, please, over to you.
Thanks, Nigel. All right. Hi, everybody. I'm Kaustav. I'm a graduate student here at IIT Bombay, and I primarily work on detecting gravitational waves from any kind of binary mergers. And today I'm going to talk about some of the stuff that I did together with my collaborators over the course of last year. And I would like to start off by showing you this plot, which shows the posterior probability distribution of the source frame total mass and redshift of the binary black hole events that have been confidently detected so far. The contours enclose 90% of the posterior probability inferred under the default parameter estimation bias used in the gravitational wave transient catalog. And just by staring at this plot, you can make two different inferences. First, most of the heavy binary black hole events are from a relatively higher redshift as compared to their featherweight cousins. And the second is the relative isolation of the GW190521 event. To remind, the May 21st event was one of the shortest gravitational wave signal observed to date. And as you can see in the spectrogram, it had a duration of roughly 100 milliseconds. And you can also see that here that the signal does not look like a typical gravitational wave chart. So the question is why? Well, to understand that, you need to look at this plot. I think everyone here knows that gravitational wave interferometers measure the differential change in the proper distance between the beam splitter and the end test mass. Or in other words, the interferometers measure the stretching and squeezing of the spacetime caused by a passing gravitational wave. Now the black curve here shows the sensitivity of one of our detectors as a function of frequency. And so the y-axis tells us how well our detectors measure the stretching and squeezing of the spacetime. In general, deeper the black curve, the more sensitive is our detector. If you look at the blue curve, which corresponds to GW150914, you can see that all three phases, namely the adiabatic spiral, the merger, and the rebound, are all within the detector bandwidth. Now, in general, a heavier binary black hole will correspond to a lower merger frequency. So if you look at the curve which corresponds to GW170729, which was a heaviest binary black hole merger before the beginning of the third observing run, you can see that it is pushed slightly towards the left. And further still is our signal GW190521, which was, by the way, observed in all the three detectors and had an estimated false alarm rate of 1 in 4,900 years. If you assume that the signal is from a quasi-circular binary, then its morphology is consistent with a mildly precessing quasi-circular binary black hole merger that left behind a remnant of 142 suns. And this makes the remnant the first confidently detected intermediate mass black hole system. By the way, an intermediate mass black hole is a black hole with masses between 100 and 1 lakh suns, I mean 100,000 suns. The value quoted here are those from a generic transient search, which to date is best equipped at detecting gravitational wave burst signals such as this. But another search pipeline, namely PyCBC, which also looks for intermediate mass black hole within the gravitational wave window, almost failed to detect this signal. And this is because of the low false alarm rate that you can see out here. And this was primarily because the detector frame parameters of the signal were close to the edge of the search space of this algorithm. So in this talk, I will tell you how we solve this problem. But before that, let me give you a broad overview of the PyCBC algorithm itself. So we kind of know what we are looking for, albeit with some uncertainty. And we also know that the signal, if present, will be buried deep in the detector noise, which is in general orders of magnitude louder than root. So model searches such as PyCBC cross-correlates the whitened detector data with that of a whitened waveform model to detect this signal. If the template is a good representation of the signal present within the data, you will see a highly peaked SNR time series, and this peak will occur close to the merger time of the signal. Since the parameters describing the waveform are not known a priori, model searches such as PyCBC, GST-LAL, MBTA uses a discrete bank of filter waveforms. At current, most model searches assume that the incident signal is well described by the quadrupolar modes of a quasi-circular non-precessing binary. And under such an assumption, it is sufficient to construct a discrete bank of filter waveforms, which is completely parameterized by its component masses and Z component of dimensionless spin. This plot here shows one such template bank in the component mass space, and it was used by PyCBC Broad to look for gravitational wave signals ranging from binary Newton star to all the way up to intermediate mass ratio in spiral in the third observing run. In fact, this is the search which reported the false alarm rate of 1 in 1 year for GW190521. As you may have realized, we need to perform this match filtering operation iteratively over a bunch of templates, some 400,000 if I recall correctly in this case. So I will call the template giving the maximum SNR as the best match template. If our template is a good representation of the signal present within the data, such as in this case, then the residual that will be left behind must be consistent with noise. And if this noise is white and stationary and Gaussian, then match filtering would have given us the optimal detection statistic. Unfortunately, however, our data is polluted with instrumental transients, aka glitches, which can also be non-stationary in nature. And to deal with them, the PyCBC search follows a multi-stage approach. It first windows out flag times of loud non-Gaussianity, and it then tries to internally identify additional times of large non-Gaussianity and zero them out using the process of auto-gating. The underlying principle behind this is pretty simple to understand. Given the whitened detector data, you look for instances where the data is significantly deviated from Gaussianity. By significant, I mean more than 50 sigma or so. If you find such an instance, you window out a second of data around the noise trigger. The first two stages are fantastic at removing loud glitches from the detected data, but there can be relatively quieter glitches that can raise false alarm. So the PyCBC search discards all triggers whose SNR is less than 4 and which is not the loudest within a given time window. And it then follows it up by performing different signal consistency tests. The first of these is the reduced chi-square test, which checks if the morphology of the trigger is consistent with the best match template. If it is so, such as in this case, then it will return a value closer to unity. If otherwise, such as in this case, then it will return a value which is far shifted to unity. Apart from that, the PyCBC search also checks if the trigger have any excess energy beyond the maximum allowed frequency of the base match template. Now, both these tests, namely the reduced chi-square test and the sine-Gaussian chi-square test, are specifically designed to handle noisy narrowband triggers. But our detectors also contains broadband detector noises, which can significantly bias our estimates of noise PSD. So the PyCBC search tries to measure any short-term variation in noise PSD and use it to correct the detector SNR. In fact, the output of all these tests are used to amend the trigger SNR in an ad hoc way so as to downrank noisy triggers. At the multi-detector level, we take clues from general relativity. A trigger, if astrophysical, must be seen across the detector network with a time delay which is consistent with the light travel time between the detectors. And it also must be described by the same waveform model. A trigger satisfying such criteria is called as a foreground trigger or candidate or an event, and PyCBC ranks them based on their relative characteristic in different gravitational wave detectors. As a final step, most gravitational wave search assign a statistical significance to a candidate by comparing its rank with those from an empirically generated background. For example, in this plot, you can see the distribution of both the foreground and the background triggers in the false alarm rate ranking statistics space. And some pipeline even reports the statistical significance in terms of the p-value or the false alarm probability. On the other hand, I will use the inverse of the false alarm rate as a metric of statistical significance. So to reiterate the necessity of a new optimized search, let me summarize the issues of the existing PyCBC based searches. As I mentioned before, The event GW190521 was hardly detected by previous PICVC based searches. And upon investigation, it was found that it was caused primarily due to two reasons. The first is the search used, namely PICVC broad, relied on the principle of finding anything as it looked for signals over a broad class of population, ranging from binary neutron star to all the way up to intermediate mass ratio in spiral. And hence it suffered from something which I'll call as the inherent search penalty. And secondly, the intrinsic parameters of the event were at the limit of PICVC's O3 range. To deal with these issues, we abandoned the philosophy of finding anything and adopted a much more targeted approach. Specifically, we designed our template bank to look for gravitational wave signals whose detector from mass close to 100 or 600 solar mass and have mass ratios in between 1 to 10, provided the secondary component is heavier than p-science. Since we have absolutely no idea about the spin distribution of intermediate mass black holes, we allowed the templates to have spins between plus minus 1. By the way, we still assume that our signal is well modeled by the dominant modes of a quasi-circular non-precessing binary, and we place the template stochastically with a minimal match criteria of 0.99, which simply means that we allowed for a maximum SNR loss of 1% due to the discrete nature of the template bank. When we search over a portion of the O3A data with this new template bank, we observe that a significant fraction of our noise triggers tends to click templates which are relatively short-lived. I think I forgot to mention that we are match filtering from 15 Hz onwards as against 20 Hz, which is in general used by other PICVC based searches. And the choice is motivated by the duration of target signals within the detector bandwidth. So in some sense, we are looking closer to the lower limit of the detector sensitivity and hence are much more vulnerable to loud glitches such as blip glitch and other sort of glitches. Therefore, we decided to remove any template whose duration is less than 70 milliseconds as measured from 15 Hz. But that in itself wasn't enough. We discovered the presence of loud, noisy triggers around the central autogated time in both the LIGO detectors. And this can be seen in this histogram. The color corresponds to the different threshold that we use in our reweighted trigger SNRs. And as you can see, there is a lot of them in both the Hanford and the Livingston detector. So as a preliminary approach, we decide to remove. I think it is better to say we decided to not consider any trigger which lied either 1 second before or 2.5 seconds after the central autogating time. Now, before proceeding any further, let me introduce you to our set of simulated signals which we use to tune and tweak our searches. All our injections are designed to mimic quasi-circular binaries with total mass between 100 and 600 suns. The signal mimicked either the dominant modes of a quasi-circular non-precessing binary, or they contain the full symphony from that of a precessing or a non-precessing binary. Now, depending on the waveform model, we distributed our injections isotropically over the spin space, and we also allowed them to be asymmetric in nature. We uniformly injected them into a data collected over the first half of the third observing run, and they are made to mimic systems that are uniformly distributed between a luminosity distance of 0.5 and 11 gigaparsec, and those which are isotropically oriented over all sky sphere and isotropically distributed over the binary orientation parameters. Now, upon performing a search with this set of injections, we found that a considerable fraction of our background triggers, which are marked by these gray color blobs, were not sufficiently downranked by that of a signal noise discriminator. On the left, we have a distribution of the noise and the injection triggers over the SNR reduced chi-square space. And to the right, we have the same in the SNR PSD variation space. So to deal with them, we decided to ignore any trigger whose reduced chi-square value and PSD variation value is greater than 10. Of course, it will lead us to miss some of our really loud injections, but astrophysically speaking, we are highly unlikely to detect such loud BBS signals, basically such loud IMBS signals with given our current detector sensitivity. So how does this changes and optimization helps us? Well, to answer that question, we use our set of injections and use them to compare our search against those of existing PICVC based searches with overlapping target space. As a primary metric of search sensitivity, we use sensitive volume time, which gives you a measure of the pipeline sensitivity. And as such, it is proportional to the fraction of injections that are recovered above a given inverse false alarm rate threshold. For our set of injections, we found that our search is approximately 1.5 to 3 times more sensitive than that of the PICBC broad search. And of course, this improvement is a strong function of the total mass of the system, as well as the threshold that we use on the inverse false alarm rate. We also compared our search against the PICBC BBH search, which by design is used to look for binary black hole systems with detector frame total mass in excess of 10 and having mass ratio between 1 to 3. We found that at really high total mass, our improvement is by a factor of 10 or more, and it is irrespective of the threshold that we use on our inverse false alarm rate, and it can pretty much seen out here. And so being happy with all the modifications and improvements made, we decided to analyze all the data collected over the first half of the third observing run and open the boxes and let the devils out. The first and the most important finding we made was the massive improvement in statistical significance of the GW190521 event. To remind, this signal was reported with a false alarm rate of 1 in 1 year by the PICBC broad search, which was used in the event discovery paper, as well as in the second transient gravitational wave catalog. So it was a factor of something like 700 improvement. However, unfortunately, we didn't discover any new IMB signals, but we reported the improvement in the statistical significance of several of the other massive stellar binary black hole events that lied within the target search space of this search. So to conclude, we demonstrated that our search within the target search space is better than all other PICBC based searches. And in fact, we even discovered that our new optimized search is far better than the other match filter based search that looks for intermediate mass black holes within the gravitational wave window, namely GST-LAL. And we also found out that this search gave comparable and in some cases even better performance than the model waveform independent search, which I think Gayatri and Tanmay are going to touch upon in their talk today. And Marek is obviously going to give a much more detailed explanation tomorrow. Apart from detecting intermediate mass black hole, this kind of search is also useful, especially when it comes to detecting highly redshifted binary black hole events. And as such, some of the newly introduced tunings in this paper are currently being used by other PICBC-based searches due to their broader applicability. With this, I will pause for any questions, and I will use this as a platform to thank all the frontline health workers and helpers who have tirelessly worked and helped during this ongoing pandemic. Thank you.
Very much. Okay, thank you very much, and thank you very much for sticking to time. All right, we've got time for questions. Does anybody like to ask anything? Okay, well, if there are no more questions, let's thank the speaker again. And then move on to the next speaker. Okay, so the next speaker is Lyudmila Fezik, the detectability of long duration gravitational wave signals. Over to you.
Hello. Thank you. So my name is Lyudmila Fezik. I will speak about long duration gravitation waves in the next 40 minutes. So there will be 2 joint talks, but after the first talk, we will have time for questions. So the first talk is about detectability of long duration gravitation wave signals, where I consider continuous gravitation waves, which is a quasi-sinusoidal emission from spinning neutron stars due to non-axisymmetric deformations or currents The duration of the signals assumed to be almost infinite, at least of the duration longer than the duration of observation data. I focus on a particular kind of continuous gravitation waves, which are long duration continuous gravitation waves, long duration, but not infinite. They're also called transient continuous wave signals. The signals that can be stopped, broken by the so-called glitches, student spin-ups in the rotation of the neutron stars. The glitches were observed systematically in the fastest young pulsar GW4 in electromagnetic observation runs. Also, glitches as effective mechanism to spin down newly born neutron stars are predicted by armored emission theory. So transient continuous waves in the case of the glitch can have duration from days to months. And typically the data is larger. For instance, one LIGO run takes more than a half year, and all the next runs going to be longer and covering more data. So if there's a transient signal of shorter, much shorter duration, but still long, at least several days, that's important to understand the difference of into statistics between the transient signal and the case when the signal is always on in the data. The signal model at the output of ground-based detector can be represented as for the case of one component as four-dimensional vector as function of amplitude parameters of the signal that includes intrinsic amplitude of the signal, polarization angles, and phase, initial phase. And the phase parameters, the frequency of the signal, and the frequency derivatives. In practice we mostly consider frequency derivatives up to the second order. If a signal is a transient, so it has a finite duration shorter than observation span and some start time, we just complete the signal model with the time parameters, the start and the duration of the transient signal. In continuous wave searches, we typically use much filtered detection statistics known as F-statistics, and firstly was constructed in the paper by Yaronovsky, Krulak, and Schutz. The F-statistics based on the maximum likelihood detection, where we maximize the likelihood function over the amplitude parameters of the search signal. The F-statistics, but actually 2F statistics, follows chi-square distribution with 4 degrees of freedom, 4 degrees, because if in the case if we consider one component with four-dimensional vector for the signal model. Chi-square distribution has non-centrality parameters that depends on the presence or absence of that signal in the data. So in the absence signal in the data, the SNR equals 0. The SNR is a signal to noise ratio. In the presence of the signal, there is non-zero non-centrality parameter. And the main question is how to compute the non-centrality parameter and how it differs for transient continuous waves. Let me firstly remind the main steps in deriving F-statistics for the case when the signal is always on in the data. This case has been derived in the paper by Yaronovsky. We assume that the noise in the detector is additive, stationary Gaussian, and there are mean random process. Then the data that includes the noise and the signal is also a Gaussian random process. We introduce the scalar products. I just briefly give them in this box on the right side. So the the projections of the signal waveform on the data is a scalar product of the data with a signal model. We speak about four Gaussian variables. And initially, these Gaussian variables are non-independent, and we make them independent with the decorrelation matrix. I also note that the Gaussian variables, firstly, the projection of the signal waveforms has a non-zero mean value in the presence of the signal of this waveform, where the mean value is a function of amplitude parameters of the signal and a covariance matrix. The covariance matrix is a block diagonal matrix of the scalar products of antenna beam pattern functions computed over the data duration. When we apply the correlation matrix, the mean value also change with the decorrelation matrix. Now the new variables that are independent Gaussian variables, and true of statistics is the sum of the squares normalized by the data duration divided by the spectral power spectral density of the noise. The SNR value, the signal to noise ratio, is the sum of squared mean values with the same normalization factor. If we consider the transient signal, when the signal not always on in the data, then we subdivide all the data duration by two parts, the part that contains only the noise and the part that contains noise and signal. I give this here the statistics based on two segments, the signal with the noise and the signal with the data. Oh, sorry, with the noise and segment with the signal. I'd like to note that if the data has gaps, we distinguish between the time span, the observation span, the signal time span, so just the end time of the data time minus the start time of the data, and the data duration. The data duration is the number of SFTs used in the data multiplied by the duration of each SFT, typically 1800 seconds. So now we consider signal projection just like it was considered for the case when the signal always on. However, now the covariance matrix computed over with the scalar products only over the signal duration. And also we have a noise, the noise projection. According to the summing rule to sum the scalar products, we sum the signal projection and the noise projection with where kappa is a factor, the relative factor between signal duration and data duration. So we get projection of a transient signal. These are four variables, Gaussian, but non-independent variables. In order to make them independent, we also apply the correlation matrix. I note that the correlation matrix, as before, it is computed with the scalar products over all the data duration. So then we consider the correlated signal projection, and I'd like to note that the mean value now consists of the composition of the correlation matrix computed over the data duration and the covariance matrix computed over the signal duration. So that's the main difference between the statistics when we compute the signal for all the data and when we compute the signal as a transient signal. So the F statistics is the sum of normalized independent Gaussian variables with the mean values that depends only on the noise, or excuse me, on the signal contribution. 2F statistics, as before, distributed as chi squared with 4 degrees of freedom, where the signal to noise ratio is depends on the normalization factor T data over power spectral density times scaling factor, which is our ratio between signal duration and data squared, and the sum of the mean values squared. I'd like to summarize together information about different and compare different signal to noise ratio for the case when we compute the signal present always on in the data, and for the case for a transient signal. When the signal is always on in the data, the SNR depends on covariance and decorrelation matrix, both computed on the data duration. Then if we compute the signal for some part of the data, suppose that starts at some start time and has some duration, T signal, but here the signal is still always on. Then our decorrelation and covariance matrices are both computed over the signal duration. Okay, I mean, the duration shorter than the data duration. And if we consider the signal to noise ratio as a transient signal to noise ratio, then these matrices are mixture. So we have a covariance matrix computed over the signal duration and decorrelation matrix computed over the data duration. We can put together this SNR, consider the relation. The zero order approximation gives us a simple relation between the SNRs when the signal is always on. And what is more important here for our study is the relation between the SNR of a transient signal divided by the SNR when the signal always on in the data. So this relation has been already derived in the paper by Briggs, Trampanis and Messenger 10 years ago. However, now we have, this relation was derived assuming that antenna parting functions are periodic with the periodicity of one sidereal day. So then if we consider long duration continuous waves with a duration much longer than one sidereal day, then we can consider this approximation. So that's true, but here I'd like to show the difference, as now we can compute the precise form and compare with the approximation. I will consider two important cases. So the first case when the data completely filled with the SFTs, so there are no gaps, and the second case when the data has gaps. As example, I took the timestamps from O1 Ligaran, where gaps are about 1 day. So there are pretty much gaps with a pretty long duration. So that's important to see how the statistics differs for the actual timestamps, actual data. So if the data completely filled, we can see that the ratio between the SNR, let's firstly consider the ratio when the signal always on. We compare the signal of shorter duration than data and with some start time, and we compute over the same duration, so perfectly matched with this duration. We consider this as function of the fixed duration and changed start time. Then we get the relation given by green points. So this relation has periodicity as function of different start times. However, we can note that the variability between the maximum and the minimum, the variability is pretty small, so about half %, so not so much difference. However, when we consider data with the gaps, this ratio gives more difference. I know that the form of this function is is just a concrete form computed for O1 Ligaran. So for other observation runs, depending on the gaps in the data, this form will be different. So I focus only on the maximum difference that we can get when the data has gaps. So the difference gets up to 8% here. So that's important to consider precise form when we consider transient signals, because if we consider a transient signal, so now let me compare the ratio between a transient signal computed over T data, but with a shorter duration. Here I present the same duration and shifted start times. So as the function, it repeats the form of the previously considered ratio, but it this is as squares of this ratio, of the ratio considered when the signal always on. And when the data has gaps, the variabilities are larger as squares. Then if we compare the same but for some different durations, for instance, if we take the duration of O1 Liger run, which is 123 days, and firstly consider the case when the data completely filled with the SFTs, we start from shorter durations and consider the maximum variabilities. They will be not more than 1.5%, and smaller and smaller for longer and longer durations. So actually for the data without gaps, the variabilities are really negligible, and the approximate form, let me at the moment go back. So this approximate form works pretty good. When the data has a gaps, we look at the right plot, and then variabilities are much bigger. As I said, it depends on the particle gaps in the data. So the variabilities can be computed for every particle gaps when we know the timestamps of this observation run. So the maximum variabilities for shorter signals, which are about, the variability is about 60% of the SNR, and going to be smaller for the longer duration transient signals. So finally, let me check if we have, so finally, if we summarize what has been done, we derived the precise form of SNR that gives possibility to make simulations, as now we know what are the signal contribution and the noise contribution in the statistics of the transient. And we can perform simulations in order to make simulation of 2F statistics of a transient signal instead of performing real searches each time. That can be important for detection efficiency. Then we found that there are non-zero variabilities and pretty large variabilities in the case when the data has gaps, just like in the real observation runs observed by Liger, for instance. So in the next talk, I will continue considering 2F statistic, but applying the template search. For this talk, please, if you have any questions, don't hesitate to ask me. Thank you for your attention.
Okay, thank you very much. Does anybody have any questions now?
I see David Catel. Hi. Okay.
Hi, can you hear me now? The mute button was not working.
I can hear.
Oh, okay, great. Yeah, nice work. Thank you. I was wondering, does this always assume that the amplitude is constant, or do you have amplitude modulation of the signal in there as well?
No, thank you for this question. I assume that amplitude is constant. But I know that in paper that by Prix, Champanis and Messenger, where was derived approximated form of the signal, the amplitude was also modulated as expansion form, exponential form. So if one interested, one could look at this. So at the moment, I have not looked into the case when we need to modulate the amplitude. Probably I will do it in the next, but at the moment I focus only the constant amplitude. But that's a good question. I mean, if somebody would surprise with this, yeah. Thank you.
Okay, thanks. Yeah, it's probably just a bit more tedious work, but yeah, doable.
Okay. Does anybody else have any questions? Anything else? No, well, if not, let's proceed to your second talk.
So the second talk about localization of long duration gravitation wave signals, so the transient signals, localization in time. Firstly, let me complete the picture that I showed before. So we spoke about statistics derived for the perfectly matched with the signal parameters waveform. However, in practice, we need to search over some frequency derivative bands, and sometimes they are pretty large, in order to search over frequency bands. So, I mean, we don't know exactly the signal parameters, of course, I mean, usually. So in order to search over frequency bands, we apply the template grid that depends on the duration, as shown here, just some function of the duration, where by duration I mean observation span. As I mentioned before, if the observation has gaps, we distinguish between the observation span or time span and the data duration. So here, when we derive template grid, we consider observation span, meaning the time span. The constants that applied to set up the template grid are found in order to get equal mismatch for any surge duration for any tau when the signal is always on. For instance, I showed my template grid mismatches for the case when we search in O1 Ligaran, which is 123 days long. I show the distribution of the mismatches, and if I decrease the duration of the searches, I get approximately the same distribution of the mismatches as it expected in the case if I set up the template grid correctly. So in this example, the mean value of the mismatch is about 5%. By the way, how to compute the mismatch? The mismatch is computed as a difference between the perfectly matched with the signal parameters to F and the loudest F that we get from the template search. But here, in the context of a transient signal, we are interested if the picture changes if we search for a transient signal, so when the signal has shorter duration than the data. Let me firstly show what is the SNR reduction function, SNR reduction profile as function of frequency offsets. So when we search with the template grid, we have some offsets from the perfectly matched signal parameters. The SNR reduction as function of the frequency offsets has been already shown in the paper by Prix about the metric. It depends on the metric of the signal. The metric is computed at the signal parameters and the offsets and frequency. Here we consider offsets and frequency dot. because our in general we in practice we consider up to the second order derivative. So here we consider frequency dot. Then the perfectly matched SNR reduction profile shown on the first picture here on the left, given by green, it's fitted with the Gaussian. The SNR reduction profile firstly derived from the metric. We know that in the case when we search over the signal duration, so for instance, when the signal always present in the data, and we search with the same duration, we have optimal template grid to search for all-time signal. Then in 10% SNR reduction, we get only one template, even if this mismatch template, so mismatch template grid with perfect signal parameters, we have only one template. However, if we consider transient signal, so the signal has shorter duration than the data, it means that our template grid has finer resolution and frequency than required to search for the signal duration. And the picture you can find on the right hand side is that in 10% SNR reduction, here and here, we have instead much more templates. I mean, much more, it depends on the duration. We have more templates than one in 10% SNR reduction. So it means that in a very small SNR reduction, so with approximately the same SNR, we have more to F outcomes, and this will participate in the detection statistics. So let me show that firstly the number of the templates computed for different transient durations. Here's the transient duration as the signal duration over the data duration, and the number of the templates on the y-axis. So we have exponential increase of the number of the templates within 10% SNR reduction if we are looking for short and short durations. Then it changed the statistics of a transient signal. So the statistics of the loudest of transient signal searched with the template grid, which is finer than the required template grid, depends on both the order statistics and the statistics of a transient. Then instead of the PDF probability density function of a transient signal, which is given here on the plot by black, we have somehow louder values for the loudest statistics, which is given here by orange. I represent on these three plots three different cases for the duration, the short, the middle, and the long duration. So everywhere here, when we speak about transient signals searched with template grid set up for all the observation span, we have louder 2F values than expected. I summarized it here for some concrete case when we deal with the transient signals. So on x-axis you see transient signals. I set up amplitudes in such a way to get the same SNR function, SNR of a transient signal computed from the statistics here together with standard deviation. However, the expected of the loudest will be larger, and it depends on the number of the templates within 10% SNR. So the statistics of the loudest is larger. So that's one of the properties of the search for a transient signal with the template grid. Another property which is useful in practice is is the fact that when we search with a template grid which is finer than required, we have somehow wider SNR reduction profile. So it means that if the reference time of the search is mismatched with the middle time of the signal, then our templates are correspondingly evolved in time. So for instance, here in the middle plot, I show the case when the mismatch equals 0. So the reference time of the search perfectly matched with the middle time of the signal. Then we have perfectly vertically alliaged in frequency on x-axis and frequency dot on y-axis. Ellipses of the same SNR reduction profile as given here. However, when we have some time mismatch as given on left plot in -10 days, the mismatch from the middle time of the signal, and plus 10 days. So then we have the corresponding evolution in the frequency that can be described by the Taylor expansion function. We can distinguish the main axis of this ellipsis as shown on schematically here, and look at the evolution of the main axis and find the mismatch in time to be 1 over the slope of the main axis. So we just we compute the difference in frequency divided by the difference in frequency dot. And we assume that frequency double dot, frequency second derivative is approximately the same. It's mostly in practice, it's true because we consider up to the second order derivative. So then our estimated middle time, T middle star, can be found from the reference time of the search minus the estimated time mismatch. The estimated time mismatch is 1 over the slope of the main axis. In practice, we can consider, for instance, here this picture when we inject the signal without any noise, then we have a perfect SNR reduction profile. However, when data has noise, so we inject a signal in the noise, the picture is a bit more complicated. But let me firstly show the process that we propose in order to estimate the middle time of the signal. So firstly, we distinguish, we collect some templates with approximately the same SNR reduction, I mean, within some SNR reduction level. We find the main axis of the SNR reduction ellipsis, and we compute its slope, and so estimate the middle time. On the plot on the right, I show the uncertainties that we get from this estimations. So the uncertainties between the actual middle time of the signal and the estimated middle time when we apply this simple process. For the case without any noise, so when the signal is injected without any noise, we have uncertainties up to 1%. By the way, I show here standard deviation of uncertainties up to 1%. If the signal is injected in the noise, then this picture, first of all, we deal, instead of the SNR reduction, we deal with 2F reduction, and picture is a bit more complicated. It has more noise disturbances. So then our estimation is worse, so about 10% for different transient durations. Let me note that if when we estimate the middle time of the signal, we can evolve back to the estimated middle time, the frequency templates. Then if we estimated more or less the estimated middle time more or less correctly, we get the picture like that, when our ellipsis is almost vertically alliaged in frequency dot space. And we can estimate from this picture the frequency and frequency dot bands where we assume to find actual signal fast parameters. So this can be applied to further searches when we localize the duration of the signal. Now, when we estimated the middle time, once we estimated the middle time, we can localize the signal duration, so to estimate the start and the end time of the signal by applying transient searches. The transient searches will be the template searches over the frequency dot bands that we estimated, and the searches with a different time duration, but with a common reference time of these searches in the estimated middle time. So as shown on this scheme, where the estimated middle time is and actual middle time is the same. So on this scheme, the first duration, actually zero duration, the initial search and all the data covered given by the first line, and all the following lines represent the transient searches when we find the first duration as the minimum span between the start time of data and the middle time, estimated middle time, or the end time of the data and the estimated middle time. We choose the minimum. In this case, the minimum with start time. So we set up the first duration, and all the following durations in time we set up such that to get approximately the same mismatch to any signal duration. So I don't cover here the question how exactly we set up the transient template searches in time, but it's simple to set up them in time to get equal mismatch. So we will keep the maximum output and the transient search with the maximum output would indicate the duration of the signal, or at least estimate the duration of the signal, indicate the start time and the end time of the signal. Let me then consider some example where I set up transient searches once I estimated the middle time. So on this picture, I show just on the bottom plot schematically the durations of transient searches starting from the initial duration denoted by 0. The transient searches, I estimated the middle time, which is mismatched with the actual middle time given by green line. The signal duration, the signal overlap of all this transient duration given by green shaded area. So we can see that for most of the cases, we deal with the transient searches, meaning that we have a transient signal for every search. So then we can find the ratio between, excuse me, it seems that my time is over. We can find the maximum SNR that we get from these transient searches. Okay, the maximum SNR I showed by the red point, and due to the initial mismatch between the estimated middle time and the actual middle time of the signal, we get the maximum somehow at somehow different transient durations than the actual duration of the signal. And this is in fact due to the mismatch in the estimated middle time. Okay, I summarize information about uncertainties in the estimation of the middle time and compare with the maximum SNR that we are able to recover. I mean, the SNR compared with the actual SNR of a signal when we compute the SNR of the transient signal with a perfectly matched signal duration and the start time. So the distribution of the maximum SNR shown here shows that we we limit the distribution of the uncertainties by the ratio by 1 minus kappa, where kappa is a signal duration over data duration. It's given on this plot. So it means that for long duration transient signals, the most important value that we get is all time duration. So this is why we limited by this ratio. For short duration transient signals, shorter duration transient signals, we're able to estimate the middle time in the noise good enough to get the SNR loss not larger than 30%. And this estimation showed that we can really apply transient searches around the common estimated middle time in order to localize transient signal in time and to get the 2F statistics on which we can decide about the effectiveness, about the signal detectability. So I think I just finish with this. So we considered how the fact that the template search for a transient signal has wider SNR reduction profile, how it influences on the statistics of the loudest from the template searches. And this statistics of the loudest is the most important for the detection statistics. And we show how can be estimated the middle time of the signal just by considering the evolution of the templates in frequency dot due to the wider SNR reduction profile. So this all gives us some tools in order to set up real transient searches for a signal when the signal duration is not known due to when the time of the glitches is not known. For instance, in the previous Ligerans to search for GW4 and also even with perfectly matched known, time of the glitches, as it was done by NICER for GW4. However, we don't know the post-glitch relaxation phase. So it means that when we search just between the glitches, we still deal with a transient signal. And so we need to understand what is the statistics when we search with the templates. So thank you for your attention. Please, if you have questions, it seems that we still have 1 minute. Thank you.
Okay, thank you for the talk. We're running out of time, but if there's one question, let's have one question.
Yes, yeah, David, please.
Okay, I hope I'm not the only one. I was wondering, again, interesting. I was wondering if the middle time of the signal that you use for everything, if that's completely required, or if you can in principle also do it with any other reference time and you just pick up some additional correction terms.
So firstly, let me point something that I just missed. When I speak about the middle time of the signal, I mean the middle time of the signal overlap. And initially, when we set up searches for transient signals, of course, we don't know middle time. We even don't know if there is a transient signal. We search with some reference time, and typically we set up the reference time of the searches in the middle of the search. So then after we estimate the with the proposed mechanism, if we estimate the middle time, we can search around the middle time, the estimated middle time. Is it answer your question, or you meant something else? David?
Yes, thank you. Somehow Zoom doesn't let me unmute. Yes, thanks for the answer. I think we can move on.
Okay. Okay, well, thank you very much for that talk. I think it is time to move on now. So let's thank the speaker again. All right, and then our next speaker is Gayatri. We're talking about intermediate mass black hole search in LIGO Virgo's third observing period.
Yeah. So let me.
Okay, thank you. Yeah.
I think you can see my screen. Okay, so let me. Yeah, so I'm Gayatri. I'm going to talk about the intermediate black hole black hole search in a LIGO runs, especially on the third observing run. So here I'm going to talk about on behalf of LIGO Virgo collaborations, and I have attached the results are based on this particular paper. So all the results you can see it more details discussion in this paper. So let me go ahead and talk about what are the interesting results that we have found in the O3 observing run compared to the previous runs. Before starting into what we have, so what we know about the black holes in the universe. So we know that we can categorize them into two categories. We known categories, that is like stellar mass black holes and the supermassive black holes. So the stellar mass black holes, as we know, they are typical, we would say the typical mass range from 3 to 100 MSEN, solar mass system, solar mass black holes. And we have several observations of these type of black holes from electromagnetic window as well as the gravitational windows. And so when we see here, this is the plot. It shows all the detected black holes, stellar mass black holes, the mass ranges we can see here, and also there how the from the electromagnetic windows are shown in the purple color, and the light blue colors from the gravitational wave window. That is the one we see it here. And also this plot also shows the neutron star, but our main distribution, we see that we have quite a lot of detections from this mass range, especially the stellar mass ranges. And then the second category, we could say that the supermassive black holes, those are the very heavy massive black holes. They are, we could say that they are, we can approximately we can find one the supermassive black holes per galaxy. But till we do there are a lot of phenomena shows that they have actively galaxies are circling around the supermassive black holes. But one quite interesting thing is that what is the black holes between these two categories? Like, what is the missing link between the stellar mass black holes and the supermassive black holes? So that category of the mass range, those black holes, we call it as the intermediate mass black holes. Those from above, the mass ranges are 100 to 10 raised to 5 solar mass black holes. So this is the detection of these black holes could solve a lot of unknown questions that we have in terms of the formation of supermassive black holes, how they can evolve, and all these things. So the looking for these black holes is very quite interesting problem from quite long time. So what we know about intermediate mass black holes. So those, as I mentioned before, the masses are from 100 to 10 raised to 5 solar mass black holes. And what are the questions? Is they really exist? Is there any reason that we should expect there is a black hole from this range? And is there evidence as of now we have, or how we can, why we will need to look for those systems? So if there is no possible evidence. So, but there are few electromagnetic candidates that shows that the black holes from this IMBH parameter space And the astrophysical origin of this remains uncertain, but there are few astrophysical formation channels that suggest that there is existence of intermediate mass black holes in order to evolve into the supermassive black holes, or they can formed due to the in a dense environment, so that they accrete more gas into the systems, and that can gain masses till the in the IMB, the intermediate mass black hole mass space. So for some of them I have shown here, and also this plot shows that what are the possible scenarios that can create a black holes that can fall under this particular mass space. And also there is a one phenomena we could call, that is the hierarchy of mergers. That's like a multiple mergers, like when in a denser environment, they can one merger of initial the first generation that call like a the two black holes from the normal stellar evolution that can form a binary, and then they evolve and then merge, and then that remnant could again form a binary systems, and then they can merge, that is the second generation, third generation, fourth. That could happen in a real time in the our we can observe those systems in a denser environment like AGNs or N clusters, or those systems we can see those binaries. So these are the possible scenario that could we could expect black holes from these system, these mass range. So, okay, so we know this. So how we can detect them? So the one way to detect them, it's looking the detection of intermediate mass black hole through the gravitational waves. So how the gravitational waves? So the system that we consider here, that is a system that is a binary, black hole binary, with one of the component mass should be greater than a 60 solar mass, and that final product should be in the final remnant mass black hole should be in the uh, intermediate mass black hole binary intermediate mass black hole system range, like a greater than 100 MZ. So that that systems could give a evidence of existence of IMBH black holes, IMBH, and so particularly these systems are very heavy, and in the current ground-based detector, these gravitational wave signals from these binary mergers will look like a burst signal. It's like a very short duration, and because of the lower limit in the lower limit of the detector sensitivity that I shown in the black curve here, that because of that we could maybe we can see signals from above 10 frequency or 15, that depends on the current sensitivity of the detector. And we can see that for the smaller black holes, we could see much longer the signals, but when it go higher and higher, we can see the small part of the signal, but it will be a short duration. Till we can see some of the signals, still maybe we can say like 1,000 or total mass of 1,000 binaries or something, we can able to see from the current ground-based detector. So, and also this plot shows that how far we can see, particularly those systems. So those are the current LIGO sensitivity, it actually peaks more, the detectability peaks around IMBH parameter space, so that we can see those systems much further away compared to the low massive systems. So this is something that the ground-based detector have sensitive to detect them. So if they are existing, then we could see those systems in the observation rates. So because of that, LIGO-Virgo collaboration has been looking for this type of systems from the 5th science run, and it started from 5th science run, and they have a lot of non-detection. So that helps for understanding the existence of these systems, and the limit, the how much the merger rate of the system could possible, that we can do it. That's how it's done as of now. And more about, I would like to mention little more about these systems, how they look like. So the gravitation waves, I have shown they have 4 plots with a different total mass of the from the IMBHP systems. So as we hear a lot from the Kaustav's talk also, there are like how we search for the systems and using the models. So typically the gravitation wave signals from the IMBHP systems, they are like not only IMBH, any binary mergers, they have 3 stages: in spiral, merger, and ring dot. So these stages actually, the inspiral part of the signal becomes shorter and shorter when it goes to higher mass ranges. And also the merger, there's a tiny part here, and then the ring node will start dominating, like play important roles when we go in higher and higher total mass of the systems. So we can see that they are look very short duration and like a burst like signals. So looking for these signals in a real noise, it's a very uh, um, very high, because we can misinterpret with the glitches. So we should have a detection criteria in order to look for these systems, very sensitive to look for these systems. So, and also I would like to mention one more thing. So we see that the amplitude of the signal also increases with the total mass, as the we see that's one more reason that this system would be the more energy, but till we could detect the signal based on the current detector sensitivity. So in the beginning of first O3 observation, that the third observing run, that LIGO Virgo collaboration detected a event that falls under the IMBHP parameter space, that is a merger of 85 solar mass black holes and the 66 solar mass black hole, and merged into a final black hole with the mass of 142 solar mass. So this final black hole actually it's fall under IMBH mass range. So this is the first direct detection from the gravitational window of the detection for the IMBH system. So this is has been shown. This we already know in the initial O3 observation run, but till we have a rest of the data, we want to analyze those with the more sensitive algorithms that are dedicated for looking for these type of sources. So to do that, we have a full O3 analysis that is approximately 0.75 years of data. The data from 3 detectors like Hanford and Livingston and the Virgo detectors. And here, not only we are using we are not using one particular search, but we use the 3 different search algorithms, and they are completely differed by their statistical properties. But the two are, we can categorize 2 into one category that is called model-based search, that Kaustav already talked in his talk. That is one of them is the PyCVC. That's how we use that particular modified algorithm where it's dedicated for the searching for the IMBH sources. And there is one more algorithm called GST Lal that also dedicated to search for the especially for the IMBH systems. And here we need to have a models, because it's a close correlation between the data and the model. So we should have a particular well modeled signals. We should have a very accurate model for these sample systems. So for that we use the SNR V4 wave approximate for this model search, and template banks are generated for the dedicated for the IMBH parameter space. So other than that, there is a one more search algorithm that called unmodeled search, that's from the coherent verbose algorithm. The one good point about this is it's a model independent, and this identification of it's based on the identifying the excess power in the time frequency domain, and using the multi-detector data. So that helps in order to get rid of the noisy triggers, because when we analyze the multi-detector using the the time delay between the different detectors, and this is more sensitive for the system that not well modeled by the template banks also, or templates that we currently available. So these three searches we use in order to analyze the full data from the third observing run. And what we have observed, we have observed three significant, so there are significant triggers, but they are some of them marginal. So the most significant triggers that event that we detected, that is the GW190521, that is already a known IMPH detection. But here we redetected them with a much more significant, because these searches are dedicated for IMBS, so looking for IMBS sources. So it should have have a more detection significance for these systems. So that is we expected, as we expected, we detected this system with the more significance. And the second source is detected on January 14th, and that is detected by the one of the unmodeled search. So CWB it's detected this is a search, and the third one is the February 14th. And this is the noise. We have did the follow-up of this event, that is noise origin. So in order to understand the other two events, we did a detailed follow-up of these events. So for the case of January 14th, when we looked into the significance of this event, we looked into two detector as well as three detector. And three detector case is more significant compared to the two detector search from the coherent burst algorithm. And also we did a detailed investigation on the noise contribution for this event due to the other environmental noise, other fluctuations, all these things. And we found that the excess vibration noise could be a contributing in a particular detector, that is a LIGO Hanford detector. But till it's not, there is a significant contributions from the Livingston and Virgo, like that could also contribute. And we could not completely rule out the existence of astrophysical origin of this event. So we also did the parameter estimation of this, if it is a IMBHB source, and what will be the parameters that we could for this event with available quasi-circular binary black holes waveforms. We found that this detector masses, the parameters are in IMBHP parameter space, but we have did this analysis with a different waveform model. They shows inconsistent results on the estimated parameter. I will show in the next slide what are how this plots looks like. And so the end, we could say we can't rule out the noise contribution also, and also we can the using the current waveforms, we could not we can't say this from the IMHB system, it's a real system or something. So this origin of this triggers still it's a debatable. And so the results, I will show it in the next slide. So the significance of the GW's 190521 event, it's shown in this table. So this is for the broader search of ICVC compared to how the IMBH targeted search, how the significance it's improved, and similarly for the GSCLAL also. And not only this search is detecting only IMBH, it's also detect the other known detection from the GWTC2. So that are the, we have mentioned.
Yeah, you've had 17 minutes, so the time's nearly up.
Okay, so this is shows the other events. They are very low marginal events, and also as I mentioned, the parameter estimated for this event, it's shown in this plots. They are not consistent in terms of masses itself. And okay, so in order to now we have did the search, but we also do the upper limit merger density study, where we use the numerical relativity waveforms in order to understand the put the estimate on what the merger density that we could expect for those type of systems. In order to do that, we inject numerical relativity waveforms from the different groups in a different parameter space, like M1, M2 space, where we can see that these are the different NR waveforms from a different M1, M2 space, and also the spinning. And also here we used a processing system also, where the spins of the black holes are misaligned. And we distributed them into co-moving volumes and then try to estimate the merger rate. Before that, we estimate the sensitive volume time, how far we can see those systems in a given volume time, and based on the loudest event threshold that is placed by the noise event, that is and based on that we can compute sensitive volume time. And that is the estimation that we have shown in this plot. This is for the all the 48 binaries by IMB's binary system we have considered for this study, and this is for the non-processing systems, and this is for processing system. And when we have a more BT, that means we can see further away. They are be sensitive to our detectors are sensitive to see further away these systems compared to the high massive systems. So and also we compute the merger rate densities based on the no detections and with detections. The estimations as shown here. So the merger rates for each non-processing and processing system shown here, and we can see that these values are very, the estimated values are like for the 100 aligned system, that is the more constrained stringent upper limit we have placed for IMBHP systems, that is 0.05 56 gigapascal cube per year. That is like 3.5.
Time's up now, so you should really just come to summary now. But
Yeah.
you've
So,
20
let
minutes.
me summarize. So we have this IMB systems are uncertain, but the detection of this system would help understanding the missing link between the stellar mass and supermassive black holes. And we have carried out the search over full O3 data, and using different search algorithm, we have reported the significant event as the May 21st event, and also the few marginal triggers and details. And also we performed the detailed merger density estimation using numerical relativity waveforms. The revised the rates has been reported in here. Yeah, thank you
Very much. Okay, let's. Is there one quick question before we move on? Okay, now I'm not seeing any questions. Okay, so let's thank the speaker again. Thank you. All right. Our next speaker is Tanmaya Mishra, who's going to be talking about optimization of model-independent gravitational wave search using machine learning.
Hi, thank you. So I'm Tanmay Mishra. I'm a graduate student at the University of Florida. And today I'll be talking about our work, which is on optimization of model-independent gravitational wave search using machine learning. This study is based on the coherent wave burst pipeline. Coherent wave burst is a gravitational wave search algorithm. It is unmodeled, as in it does not depend on modeled waveforms. Instead, it looks for excess power in the time frequency domain. On the figure in the right, you can see the time frequency slices from Virgo, Hanford, and Livingston detectors. And what CWB does is it extracts the excess power and reconstructs the waveform and estimates a bunch of summary statistics. This example is for GW190521, which is the IMBH event that Kostov and Gayatri were talking about. As they pointed out in the previous talks, As we move to more massive systems, the signal duration becomes shorter, and so short detected glitches can actually mimic those signals. In the standard CWB search, we have something called as the standard veto method, which is basically using a bunch of a priori defined thresholds on summary statistics that helps us in distinguishing between noise and signal. In this study, we propose to use a machine learning method to improve this separation between noise and signals. So before we go ahead, let us look at the veto method limitations. In this plot, we can see on the left distribution of noise events and signal events before application of any vetoes. On the right, we have the background and noise and signal distribution for after application of vetoes. So what we can see that most of the noise events are discarded by the veto method. An example would be CC greater than 0.7, where CC is the network correlation coefficient and is one of the CWB summary statistics. The problem is that we risk losing some of the signal events that do not make the threshold. And we can see that some noise events make it into the signal event distribution because they have passed the thresholds that are put on the summary statistics. So, and these can be treated as real events. Moreover, designing these vetoes is a time-consuming and complex process. Using machine learning, we can actually get a continuous ranking criteria for each of these events, and we can automate this standard veto method procedure. So what we're looking at is a problem of binary classification, and it is widely known as the machine learning community. So in order to use machine learning, what we do is we carefully select a subset of summary statistics that CWB estimates, and we use that as the list of input features for the machine learning algorithm. Since the list of machine learning algorithm is in order of 10, we do not look at deep learning or neural network, which is harder to set up. We instead look at simpler decision tree based machine learning algorithms. And we found that extreme gradient boosting was the most efficient for our problem. XGBoost creates a forest of decision trees, and a decision tree is given in this illustration on the right. So it has a root node which splits into decision nodes, which further splits till we reach a leaf node. So what we do is we pass all these CWB events through the decision trees, and they end up in one of these leaf nodes. The output that we get from this machine learning method is called WXGB, and this is a continuous value that goes from 0 to 1. 0 meaning it is most likely a noise event, and 1 meaning it is most likely a signal event. Here is the list of the CWB summary statistics that we have used as the input list of features for XGBoost. We use coherent SNR, central frequency, correlation coefficient, and so on. So the way we do tuning and training is that we first structure the data as shown here. We label every noise event as 0 and every signal event as 1. And we allow tuning by doing a grid search over 5 XGBoost hyperparameters with 10-fold cross-validation. Once we do tuning, we fix the XGBoost hyperparameter values, and we train and test a separate model for each observing run and search configuration. The way we divide data into training and testing is that for each chunk of LIGO Virgo data, we randomly select 100 years of background data and 1,000 simulation events for training, and we keep the remaining for testing. We also propose a new detection statistic. We do not directly use the machine learning output WXGB as the detection statistic because it can claim significance for low SNR events. So what we do is we use coherent energy, EC, which is a summary statistic estimated by CWB as the primary detection statistic, and we use WXGB and chi-square as penalty factors. The detection statistic expression can be seen here. Before we go further, let us look at false alarm rate and detection efficiency to understand the results. So false alarm rate gives us the significance of the event. It is calculated as the number of reconstructed background events with the test statistic greater than a threshold divided by the total time of background data in years. And the detection efficiency is defined as the ratio of the number of recovered simulation events with far less than a threshold divided by the total number of recovered simulation events. As Gayatri was talking about, the different types of searches, we have stellar mass BBH search, which looks at systems systems with total mass less than 100 solar masses, and the intermediate mass black hole search, or the IMBH search, which looks at systems with total mass greater than equal to 100 solar masses. We divide these searches in the frequency band. For BBH search, we look at frequency from 60 Hertz to 300 Hertz. And for IMBH searches, we look at everything below 200 Hertz. Let us look at the results. So these are the results from observing run 1 and 2. We plot the detection efficiency versus false alarm rate plots, and detection efficiency at far less than 1 per year versus central frequency. The red curves denote the machine learning aided CWB search. The blue curves denote the CWB search with the standard V2 method, and the green denote the CWB search without any V2s or machine learning. The solid lines correspond to the BBH search, and dotted lines correspond to the IMBH search. So as we can see from all these plots that the machine learning aided search improves the sensitivity of the searches. And for BBH, it is around 25% at far less than 1 per year. And for IMBH, it is the improvement is around 15%. Before we go further, we also did a test of robustness. That is, we do not want the algorithm to be sensitive only to simulations that lie in the training simulation set. So in order to test this, we trained the algorithm on circular orbit binaries, and we tested it against high eccentricity binary black hole data with eccentricity values as high as 0.75 to 0.99. And from the figure on the right, we see that the machine learning aided search is still sensitive to eccentric orbits data when trained only on circular binaries. And it is improving the sensitivity compared to the standard search. From this, we can conclude that XGBoost is robust enough to detect simulations that lie, to detect signals that lie beyond the training simulation set. We also did a network comparison with the 2-detector network HL, Hanford and Livingston, versus the 3-detector network HLV, which is Hanford, Livingston, and Virgo. We did this on O3A BBH run on one of the chunk data. As we can see that these have different lifetimes and different background years available. So what we did for fair comparison, we looked at injections only in the common lifetime, and we selected the same amount of background years for training, that is 550 years. And moreover, we divided the injections into training and testing based on equal intervals of GPS times for fair comparison, and then looked at the recovered sim using machine learning approach. Let us look at the highlighted events here, and we can see that for say 5,700 injections, we recover around similar amounts for both the detector networks. But what we observe is that higher significance at I for 1 year or for 1 per year. We see that the 2-detector network does better than the 3-detector network. We have around 5% more detection compared to the 3-detector network. This is the detection efficiency versus FAR plot, where the dark red and dark blue correspond to the 2-detector network, and the orange and the light blue curves correspond to the 3-detector network. We find that machine learning works for both the detector networks, and it improves the search sensitivity for both of them. However, the 2-detector network is still performing better than the 3-detector network. This is primarily because Virgo brings in more noisy data and is less sensitive than LIGO and Hanford and Livingston detectors. Now let us look at the detections. This is from the GW4 catalog for O1 and O2 observing runs. On the left, we have the standard search CWB significance, and on the right, we have the machine learning aided CWB search significance. we can see that for each of these events, we have improved the far, we have improved the significance. Moreover, we also recovered GW170809, which was previously missed by the CWB search because of a standard veto. We do the same exercise with the first half of the third observing run, O3A detections. And the standard search detected 15 events in O3A, but with the machine learning aided search, we now recover 17 events. We have recovered 3 extra events that are present in GWTC2, but were missed by the CWB search previously. Again, we noticed that using machine learning, we have improved the significance for each of these events. One event, for example, is the IMBH event. It had a significance of 1 in 4,900 years, as Costa pointed out. But now, with the machine learning, it has far less than 1 per 10,000 years. We also detected a trigger with far less than 1 per year, but it was removed by the sub 60 Hertz clean data. So in summary, we can use machine learning to automate the standard veto method, CWB's standard veto method. At the same time, we can improve the search sensitivity to different searches. Extreme gradient boosting appears to be the most suitable choice for CWB. And from the results, from observing run 1, 2, and first half of observing run 3, we have detected all the previously detected events by CWB with higher significance, along with 4 new events that were previously missed by the search. XGBoost is robust in the sense that it can detect signal that do not lie in the training simulation set. The 2 detector network appears to be more favorable than the 3 detector network, even after using machine learning. And more details about O1, O2 results can be found in the paper here. And thank you, and I'll be happy to take any questions.
Okay. Thank you very much. Any questions anybody would like to raise? Any?
I think we had a hand up from Odyssey.
Who had their hand up? If any, yeah, please just unmute and ask if you have a question.
Hey, Tanmaya. That's a very good work anyway. And by the way, I'm just curious about the test that you have done for LP versus HLP. That it shows the efficiency, the number of recovered events is greater for a given IVAR is greater in HL than HLP. I guess it's order 1,800 versus 1,700. I don't remember.
Right.
Yes, this one. Yeah. So I'm still wondering actually, like, so basically, given in that way, so the same, let's say, triggers have lower significance in HLP than in HL, let's say. So I mean, because what I have studied, basically, if this means coincidence analysis, usually like triple coincidences will give better significance. So this means that the somehow time coincidence here is not so dominant, let's say. Can you comment more about this?
Yeah, so the first point is that we looked only at common lifetime injections, which is why the recovered sim is around the same for both the networks. Otherwise, in principle, HLV should be sensitive to more events. It should have more triggers. But what we see is that at higher significance, the 2 detector network is still performing better than the 3 detector. And I think what we would expect is that 3 detector network to have more significance and to be more sensitive, but I think we need to retune the CWB pipeline in order to get that. But at the current stage, adding Virgo adds a lot of noise to the data, and so the significance is not exactly improved. Does that answer your question?
I agree. That's with Virgo, with noisy data, that adds more noise, let's say. But let's say I'm just in a sense. So if let's say HL two triggers in coincidence and then one B, but in coincidence from noise, that's lower the significance. But I mean, if the three should be real injections, yeah, it's just I'm just wondering because in my intuition it's like it should be somewhat giving higher significance, but maybe I should think better about this. And yeah, thank you, by the way.
Okay, thank you.
Okay, thank you. Are there any other questions? I'm not. Okay, well, let's thank the speaker again.
Thank you.
And then let's move on to our next speaker, is Scott Field, Learning Orbital Dynamics of Binary Black Hole Systems from Gravitational Wave Measurements. Okay, please go ahead.
Sure. Screen up? Can people see the screen?
Yeah, it's come up now. Yeah, okay, great.
Oh, it's good. Okay, great. Thank you. Yeah, so this talk will be switching gears a bit. It's talk about an application of machine learning to modeling binary black holes. So this work is based on this paper that we've uploaded to the archive a few months back, done in collaboration with Brendan Keith at Lawrence Livermore National Lab and Akshay, who's a grad student at University of Mississippi. Not only did they collaborate on the paper, also the talk as well. Some of these slides are just slightly modified versions of ones that they've given in past talks. Thank them for that. So a brief introduction to the problem. So this is somewhat of an obligatory figure showing areas of systems. And over in the figure, we see that there are numerical variance, mass ratios, and orbital separations. The code's run and robust and can generate lots of waveforms. The higher mass versions numerically become, although this that front typically they use black hole theory, spiral, also orbital separations, any other models, for example, effective one body, more recent backbone body. There's a phenomenon family of models. Each of these in some starts in where you start versions, you make approximations so you can derive tractable ones, can actually solve them. So the invert that method. So we have starting division of some information that we mix and then generate waveforms. The arrows can flow this way.
Okay.
Sorry, I think you're muted.
Yeah, somehow, sorry about that. I think I lost somehow connection, and now Zoom decided to mute me. Okay. Is the audio back?
Yeah, we
Yes.
can hear you now.
Okay, great. Hopefully there'll be no more glitches. Sorry about this. Okay, so the proposed learning strategy, which is in somewhat generic and can be applied to other scenarios, is to propose some ordinary differential equations that one may think would describe the two-body dynamics, parameterize these ODEs by deep neural networks, which are known to be good approximates for various nonlinear functions, and then propose a constrained learning, physics-informed constrained learning optimization problem to train the ODE model to match the dynamics that are generating the gravitational waveforms. So one thing to keep in mind is the many of the equations that we'll be seeing in a bit are quite simple, certainly by the comparison of post-Newtonian or effective one-body equations. But this is really just to demonstrate a new computational method. But we'll also see that these simple choices lead to fairly accurate models, largely because the complexity is hidden in these neural networks, which are known to be good approximates for general nonlinear functions. Okay, so just a quick bit of terminology. So we'll be using some technique called universal differential equations. So we want to know what those are exactly. They are basically neural ODEs, so ordinary differential equations that have neural network terms that have more physics baked in. So this is just an ODE that is the usual form. It's the time derivative of x equals the right-hand side, which depends on the dependent variable x, as well as this neural network here that we have to train. So these are parameterized by unknown parameters. This idea was introduced fairly recently in 2020 by Rakakis et al. And the idea is to pick some ODEs that have some expected physics, but you're not actually sure what the missing physics will look like. And you parameterize this sort of ignorance of what the physics should be by these neural networks. So why neural networks? I mean, there are really two reasons for using them, I suppose. One is there is some theory, largely speaking, going under the term of the universal approximation theorem, that neural networks can approximate smooth functions arbitrarily well, as long as your networks are sufficiently deep. And just in practice, neural networks have somewhat of a magical property of you're able to over-parameterize these functions by lots of unknowns, and using robust training algorithms, model unknown features or unknown functions without overfitting. So that's another reason for using them. They just appear to work very well in practice. So just as an example for some concreteness, so what are universal differential equations? Imagine you knew you had some model, x and y, they depend on time, and you happen to know one of the terms in the ODE. So here we just have these two terms in blue, but you knew that there was some missing terms floating around. You would parameterize this by two different neural networks, F1 and F2, and propose a training algorithm for finding the neural networks, training them, getting these network parameters such that the trajectories that you generate once this has been trained matches the observation. So you have some trajectory data that you're trying to match. So you're trying to minimize some cost function shown down here to kind of achieve this matching. So the model we'll be looking at is, again, exceedingly simple. It's largely Keplerian dynamics plus neural network terms. So we imagine we have non-spinning point particle black holes of mass 1 and 2, and motion is just in the XY plane. And actually, a lot of these parameters just come from what the geodesic equations are in Schwarzschild. If you look in Chandrasekhar's book, for example, so you have an angle phi between the orbital separation vector r and the x-axis. There's this relativistic anomaly that parameterizes sort of the, you can see it actually show up right here, the effect due to eccentricity, the oscillations in r. The semi-lattice rectum and the eccentricity, these are two other orbital parameters. But the point being is once you have these four written down, which in some sense is describing an effective one body, you can form this separation vector, which is a function of time. And then from that, get R1 and R2 using just standard kind of Newtonian formulas. So largely everything about this picture is very much like Keplerian. But we add to it terms that parameterize missing physics, which is the sort of relativistic terms that we're hoping to capture. So in each one of our dynamical equations to the right-hand side, we add a calligraphic F. There are 4 different deep neural networks here that we have to find. They're functions of the dynamical parameters themselves, but also unknowns. And here's an example of a very simple neural network. So there's this unknown weight W, a bias B. This is the sigmoid function. You can use other activation functions. The ones that we use are more complicated than this one, but this one's just easy to write down on paper. And we also use an exceedingly simple orbital map, just quadrupole formula, to go from trajectories to the measured waveform. So the goal here is to find F1, F2, F3, and F4. And for that, we have to solve a constrained optimization problem. So this is where the tricky part comes in, because the waveform that we're generating implicitly depends on these network parameters. So that's given down here in the bottom left. And we're trying to minimize or match the delivered waveform with the neural networks to some observation that we have. So we have to solve this minimization problem. It's a constraint, subject to the constraint that it solves the ODE, the trajectories. So a bit about the training. How do we actually do the learning here? So we initialize the parameters to be 0. That's obviously not going to be the right choice for the neural networks. Then we evolve the system forward in time to get our dynamical variables from which we can get the binary black hole trajectories. From that, you can use any formula. Here's just the quadrupole formula to generate the gravitational waves. And then finally, you calculate the difference between your predicted waveform and the measured waveform. At least on the first pass, this is going to be not very good, because if all the neural network terms are 0, this is not relativistic physics, so the error will be large. But the idea is that using this method called the adjoint sensitivity method, in addition to an optimization algorithm known as BFGS, you can update your neural network weights and iterate over this inner circle here until you achieve sufficiently accurate waveforms, which is to say you found a dynamic model which generates waveforms that agree with the ones that you're actually measuring. And then you can use the model to do things. So it's an ODE, and so you can evolve it forwards in time, much longer than you actually did over your training window, for example, because you have a fully working dynamical model. Okay, so a couple of quick examples. So the first one is I'll call a sanity test. So anytime you have something new going on, you just want to check that it can do even simple things. So here is, we're just looking at geodesic motion. So if mass 1 is much greater than mass 2, mass 1 is fixed at the origin and mass 2 is just following geodesic motion. So E dot and P dot are equal to 0. And we want to recover missing terms. So the true model, the ones that are describing the orbits, are given here. And you can see there are these red terms that are the missing terms, because if we compare with the universal differential equation model here on the right, if these F's were 0, we wouldn't be recovering those terms. We would match these prefactors, which is effectively the Newtonian case. So that's what we're after. And here's the first result on this sanity test. So we provide to the algorithm these black dots here, which are samples of the waveform over just a couple of orbital cycles. And from this, we can run that learning algorithm that we just described a bit earlier until we've achieved some accuracy threshold level that we're happy with. And once we're done with that, we can plot it. And actually over here, you can see the black lines here is the orbits over which this training procedure appears. And then we can ask, well, what happens if we use this model much further in time? So we integrate it basically over a 4 times larger time window. So the orbit continues, and actually you can see here the true waveform, and here the true trajectory is given by these blue lines. So the waveform down here and the trajectory over here. And then using our universal differential equation that we've just trained matches reasonably well over even longer extrapolated windows of time, which is somewhat unusual for machine learning algorithms. Typically, you don't want to extrapolate. You only want to work in the training interval that you've applied, but somewhat surprisingly and fortunate for our case, these ODE models appear to extrapolate fairly well in time. Also, comparing the true model to the universal differential equation model, we can compare the right-hand sides, because this is the one that was hidden, and now we have one that's recovered. So we can compare the right-hand sides of phi and chi just to ask how close are they to one another. And that's the relative errors given down here in the bottom right. You can see that they're very small, basically 0.1 to 0.02, 0.01 to 0.02, which also describes, or at least gives insight as to why the model can be extrapolated much further in time. We're kind of correctly capturing the right-hand side term. So in this case, we started out with just Newtonian dynamics. Again, this term for 0, this would be Newtonian dynamics. And the universal differential equation model, after trained on one waveform, was able to learn the relativistic corrections needed to carry out even longer integrations. So a more challenging case is equal mass quasi-circular orbits, because now we have radiation reaction, and this will drive an in-spiral process. And this is a spec simulation that we use for our training data. So we took a spec equal mass circular orbit, quasi-circular orbit waveform that's given down here as the black dots, the data. And one thing to note is the optimization procedure here. We've had to add in a bit of regularization and also add in more physics-informed constraints to the optimization problem. So for example, we know physics tells us the orbital separation vector should shrink due to in-spiral, and that's something that's actually been added into the constraint optimization. But largely everything proceeds as we described a little bit earlier. And once the training procedure is done, well, we can at least compare the waveforms, because we have the original data, and then the fit one is the one delivered by the model after the dynamical model has been trained. So at least visually, they agree very well. And you can even do a more careful comparison using a LIGO type L2 kind of norm and overlap error. So here we've compared the waveform delivered by the universal differential equation model and compare it against two other models that actually we heard about earlier today, the SCOB and RV4 PHM model, and then a numerical relativity surrogate model. The universal differential equation model has errors that are a bit higher than the EOB one, and probably about 2 orders of magnitude higher than the NR surrogate one. But that being said, certainly many of the choices we made are very simple. So for example, the quadrupole formula, certainly not correct. That can be swapped out for a better model. And these other models, the EOB and the surrogate model, they've been in development for decades, whereas the universal differential equation model, this is just proposing it for the first time here, but already we're able to get fairly good waveform accuracies. And then we can also do things like just visually check the trajectories. So this black curve here, which is kind of hidden below the blue and the orange, that's the NR trajectory, which admittedly is not in the same gauge as our model. So spec uses a damped harmonic gauge. But I think just looking at this, you can see that at least our model's, roughly speaking, capturing the NR trajectories, which is something that other authors have looked at in the past. For example, when comparing PN or even EOB trajectories to NR, there seems to be some remarkable agreement between the NR trajectories, despite the fact that they're not actually computed in the same coordinate system that the model is defined in. So that's something we also observe here. Another thing we can do is look at the orbital phasing. So here we plot the accumulated orbital phase as a function of the orbital frequency. So the NR data is sort of given in this inset panel here. So you can see how the orbital phase accumulates with increasing orbital frequency. And we can compare this to, again, our 3 models. So the EOB model, the NR surrogate model, and the UDE model that we just trained, and just ask how well did they agree. And that's given by this main plot. And you can kind of see just by looking at the y-axis scale, but all 3 models have very good tracking of the phase throughout these last 20 or so orbital cycles. In fact, I mean, the figure ends here when a common parent horizon is found. So they're all doing very well, even up into this highly nonlinear regime. The last example I want to conclude with is a slightly more challenging case where we have an eccentric binary black hole simulation where we add a little bit of Gaussian noise. And the procedure is exactly the same as before. We're just looking at how robust the model is to adding some small amount of noise. So down here, you can see the waveform data. So these black dots are basically it's the SXS data, but with small Gaussian noise added in. And this orange line here is the waveform generated by our model after training. So you can see they agree reasonably well. And then we also, just for fun, we show the imaginary part. So this is the 2-2 harmonic mode. So there's a real and imaginary part. And the model has never seen this, but it also matches the SXS model reasonably well, at least in the eyeball norm. And then again, here on the right, we can sort of look at the orbital trajectories and even plot differences just to kind of show things are on the right track. But again, these trajectory quantities are coordinate dependent. So we're just kind of looking for broad visual agreement here. And then the final thing is how robust is the algorithm to increasing values of the SNR or decreasing, rather, increasing noise. So in this figure here, we plot the SNR on the x-axis, starting from extremely large SNRs, which is probably the regime where if you just have clean numerical relativity waveforms, and what happens when you add an increasingly large amount of noise, the SNR goes down, how well can the method continue to work? And we quantify this by comparing the true NR waveform, so not the one that we've added noise, but the one that's buried in the noise, to the waveform that our model is able to generate or fit to after the training procedure. So you can see there's certainly a rise that continues as the SNR gets lower. Typically, this 10 to the -2 number is quoted by many modelers for the threshold where you have good models where it's below it, not so good models where it's above. And you see the crossover here is roughly SNR 50 or so. But nevertheless, so I mean, there's maybe some improvements that we would need to use to apply this to many of the LIGO events that we've heard about today. But we're actually surprised it worked at all, even when the SNRs were this small. Okay, so I think I'm probably just running out of time, especially with the technical difficulties. So we're basically at the end here. So in this talk, we proposed, it's a computational technique. So it's a new computational technique or tool for finding differential equations given waveform data. This technique is independent of modeling choices. So the modeling choices we made are simple, although they were able to deliver fairly high quality approximations to the orbits and also the waveforms. But for example, you could swap out the quadrupole formula for PN formula. You could swap out the ODE model that we used for PN, for EOB. It's largely agnostic to those choices. And the main thing that's sort of new is that we augment the dynamical equations, the on-stop model, with deep neural networks, and then we solve it with this joint sensitivity method using a constrained optimization problem. We looked at a couple of simple test cases here. So future outlook, so this is a new method, so there could be many uses for this. Hopefully, there are many uses for this. The obvious extensions are to including spin, for example. Personally, I think the thing I'm most interested in is its ability to maybe supplement other modeling efforts, all of which typically have unknown terms that need to be calibrated. So PN, EOB, the backwards one-body model, NR surrogates could potentially all benefit from some approach similar to this one. And then to use it on realistic LIGO data, if one wanted to do that, basically the challenge would be extending the methodology to work at SNRs below 50. Some ideas we had for that were using Bayesian neural networks instead of the kinds that we had, which may be more graceful for dealing with noise. You could also look at, for example, denoising techniques that many people have explored in the past to kind of pre-process the data, or maybe looking at a collection, an ensemble of signal detections, which may be also be able to give you better resolution. Okay, so I think that's pretty much it. Thanks.
Okay, thank you very much. Thank you. Thank you. Are there any questions? If anybody's got any questions, please just unmute yourself and ask it.
If there are no questions, I can also a short kind of plug for the code. So the code is all uploaded on Zenodo. It's written in Julia, which was really my first experience using the Julia programming language. It's very Python-like, but appears to be much faster, and has implemented a lot of these machine learning tools that we've used. So if you're interested in this, maybe the best place to start is just downloading that Julia code and running it on your laptop.
Okay, and you, I think earlier, I mean, this will all be recorded and people can see it. You put a paper reference at the beginning, as I remember.
That's right, yes. The paper is on the archive, and the link to the Julia code is embedded somewhere in the paper. Okay,
so if anybody wants this, they can just come back after the when the recordings are made available and go to that archive number.
Sure.
Okay.
Yes.
Let's thank Scott again.
Thank you.
Thank you. All right. So our final speaker this session is is Mikhail Klopinov. Okay, here we are. and you'll be speaking about odd-dimensional gravitational waves from the binary system. Okay. On the three brane.
Can you see my screen?
All right. Yes, I can hear you, and I can see your I can see you shared screen successfully.
Okay, thank you. I will speak about the odd-dimensional gravitational waves from the binary system on free brane. And to motivate this work, over the last 2 decades, a number of gravity theories with extra dimensions of space-time have been developed. However, the characteristics of extra dimensions within these theories, such as the number of extra dimensions, their size and geometry, vary widely from one theory to another. But the developing gravitational wave astronomy provides one of the most promising tools to probe the extra dimensions and their characteristics. So the detailed study of gravitational radiation within the extra dimensional theories is of main importance. For example, the first constraints on the characteristics of extra dimensions has already been obtained by use of the gravitational wave data. Also, another promising tool to probe the characteristics of extra dimensions is provided by the first photograph of supermassive black hole shadow. And also, the multidimensional radiation theory finds its applications in a holographic description of quark-gluon plasma and field theoretical models in condensed matter physics. But here we will consider the gravitational radiation. Also, only the even-dimensional gravitational radiation has been discussed in the most of literature, and this is due to the violation of Huygens principle in odd dimensions. The best way to illustrate it is to consider the retarded Green's functions. So, the retarded Green's function of the D'Alembert equation in d dimension is given by the following equation and provide us with the retarded solution of the D'Alembert equation defined in a standard manner. Solutions to the given equation are given by two recurrent relations separately for even and odd dimensions. While in even dimensions, the retarded Green's functions are given by the combinations of delta functions and its derivatives localized on the light cone. In odd dimensions, retarded Green functions are given by the combinations of Heaviside functions and their derivatives, leading to the localization of the Green functions, not only on the light cone, but also inside it. Therefore, the retarded fields in odd dimensions propagate in space with all velocities up to that of light, depend on the prehistory of source's motion preceding the retarded moment of time, and diverge on the light cone. This can be seen from the structure of retarded Green functions, for example, in 3 and 5 dimensions. Therefore, the extraction of emitted part of the field, of the retarded field in odd dimensions in standard manner becomes highly non-trivial and requires a more sophisticated approach to definition of radiation. And such approach was suggested by Rohrlich and Teitelboim, and it is based on the use of certain covariantly defined quantities. Let us consider the point particle moving along an arbitrary world line. And let us consider the observation point as the top of the light cone in the past. Then the moment of particle's proper time corresponding to the intersection point of world line with the given light cone is called the retarded moment of proper time and is given by simple equation. Further, all the headed quantities will be assumed to be calculated at the retarded moment of proper time. Then we can introduce the following d vectors. The first one is the light-like vector, x capital, which is directed from the retarded point of world line to the observation point. The second one is the unit space-like vector u, orthogonal to the particle's world line. And the third one is the light-like vector c, which is aligned with the vector x capital. This the vectors has the following properties, and also we can introduce the scalar Lorentz invariant scalar parameter rho defined is given by this equation, and it is equal to the spatial distance between point particle and observation point in the Lorentz frame moving with the point particle at the retarded moment. And also this Lorentz invariant parameter rho is equivalent to the spatial distance when the observation point is far from the world line. Therefore, in what follows, it is the Lorentz invariant parameter 1 over rho will be used to obtain the long-range part of the tensors and for the definition of the wave zone in Rohlich-Teitelbaum approach. Rohlich-Teitelbaum approach is based on the splitting of the on-shell energy momentum tensor of the retarded field instead of the splitting of the retarded field itself. And in d dimensions, this on-shell energy momentum tensor of the retarded field can be expanded in the inverse powers of Lorentz invariant parameter rho as follows. The first one is the energy momentum tensor of the deformed Coulomb part of the field. The second one is the mixed part of the energy momentum tensor, and it consists of more than one term in dimensions higher than 4, and it is absent in dimensions 3. And the last term is a long range part of the on-shell energy momentum tensor, and it has properties which allow us to associate this part of the energy momentum tensor with the energy momentum tensor of radiation. Indeed, this part of the energy momentum tensor is conserved separately from the other parts of the energy momentum tensor. It is proportional to the direct product of two light-like vectors, which corresponds to the propagation of this part of energy momentum of the field in space exactly with the speed of light. And also this part of the energy momentum tensor gives positive definite energy momentum flux for the distant sphere. Given all these properties, we can define the flux of radiation energy through the distant sphere in standard manner by the integration of long-range part of energy momentum tensor over the distant sphere. However, in odd-dimensional case, this radiation power depends not only on the state of source at the retarded moment of time, but on the entire history of the source motion preceding the retarded moment of time. In our work, we consider the binary system of 2 point masses moving under the mutual scalar interaction and localized on the free brane. The action of such system is given as follows. Here, indices in brackets denote and numerate the world lines of particles, and sigma are coordinates on the brane, and gamma is the induced metric on the brane. By standard procedure, we obtain the gravitational fields equation of motion and the matter energy momentum tensor localized on the free brane. In our case, energy momentum tensor consists of 2 terms. The first one is the energy momentum tensor of the point particles, and here we used the point particles world lines in terms of the bulk coordinates instead of brane coordinates. And the second term is the energy momentum tensor of scalar field localized on the brane, and we know that this energy momentum tensor has a distributional type singularity, which corresponds to the localization of scalar field on the free brane. Also, we obtain the scalar field and point particles equations of motion. And in case of scalar field, it's just the inhomogeneous D'Alembert equation on the curved free brane. And the equation of motion for point particles is just the geodesics equation on the brane in presence of the scalar field. Also, we note that the presence of the scalar field shifts the masses of point particles living in the brane. In what follows, we limit ourselves to the consideration of the small metric perturbations over the background Minkowski space, leading to the expansion of metric tensor as follows. And we will simplify equations of motion, of gravitational field, and of matter on the brane by use of the following assumptions. First of all, we assume that binary moves inside flat brane, inside flat free brane, and it doesn't affected by the gravitational waves produced by the system, and energy density of the point particles and scalar field doesn't contribute into the background curvature. So the induced metric on the brane is just the flat Minkowski metric. We assume that our flat free brane is placed in the x4 equals 0 plane, and the coordinates on the brane are aligned with the bulk coordinates. Also, we assume that particles are non-relativistic and are spatially separated enough, so we can neglect the shift of the masses of point particles by the scalar field. And the last assumption is that we assume that scalar field just governs the binary orbital motion and it doesn't contribute into the radiation processes by the binary. Then we can neglect the self-interaction terms in the equations of motions. Here, lower indices at the scalar field is just the scalar field, denote the scalar field produced by the particle with number k. And here we neglect the self-interaction of point particles with their scalar fields. Then our equations of motion for the point particles reduce to the some analog of the Newton equations on the free brane, and scalar field equation of motion reduces to the D'Alembert equation on flat free brane. We also obtain the metric perturbations equation of motion in the Lorentz gauge, where we introduced the H-bar tensor in an ordinary manner. Also, expressions for energy momentum tensors of point particles and scalar field are also simplified significantly, and we obtain that our scalar field energy momentum tensor is proportional to the delta function corresponding to the localization of energy momentum of scalar field on the free brane. And we also use here equations of motion for the point particles and scalar field. Gravitational waves generated by such a non-relativistic binary, are given by the retarded solution of the equation of motion for the gravitational field, and it consists of two terms. The first one is the contribution from the point particles into the gravitational field, and the second one is the contribution from the scalar field, energy momentum tensor. And the 5-dimensional retarded Green's functions is given as follows. According to the Rorley-Teitel-Boehm approach to the radiation, we will consider only the emitted part of the metric perturbations energy momentum tensor, which is calculated in the transverse traceways gauge. It has this very simple form, and the transverse traceways gauge is computed by analogy with Weinberg textbook, for example. And here we note that we can calculate transverse traceways part of the fields of the Lagrange part of fields derivative, because derivative of the lambda tensor doesn't contribute into the Lagrange part of the field. and lambda tensor is a bit modified due to the increased dimensionality of the space-time. So in the transverse traceless gauge, the generated gravitational waves will have 5 independent polarizations. For example, if we consider the gravitational wave propagating in the Z direction on the brane, then its field will have the following simple form. Here we can see 5 independent polarizations defined as follows, but we note that the brane-leaving observer would detect only 3 of these polarizations. The 2 standard plus and cross polarizations, and the predicted earlier, the breathing polarization. Before calculating the contributions of point particles into the gravitational field, let us consider as most simple but very instructive example the problem of scalar radiation by one point particle. Equation of motion for the 5-dimensional scalar field interacting with a massive point charge has a form analogous to the obtained earlier, and its solution is given by the simple integral. In our calculations, we use the canonical energy momentum tensor of free massless scalar field, which has very simple form, and then solution of the 5-dimensional equation of motion for the scalar field is given by the following integral. It's integral over the proper time of particle. Then, according to the Rorlich-Taiteli-Boehm approach to radiation, we extract the long-range part of the scalar field derivatives from this integral, and it is obtained in the following form. We know that only the first term in this integral amplitude contains all the physical information concerning the properties of scalar field in the wave zone, and the last 2 terms.
Sorry to interrupt, the time's nearly up. You got 3 minutes left.
Oh, so then just keep the details. We can expand the obtained integral amplitude in the non-relativistic limit and obtain the following form depending on the entire history of particles' motion. It depends only on the third derivative of particles worldwide. Then, in accordance with the scalar case, we can find in the non-relativistic limit the emitted part of the gravitational field produced by the point particles. It's given in square, and we calculated it in the center of mass frame. Now we can turn to the contribution of the scalar field. It can be obtained in the following form, taking into account the properties of the lambda tensor, and we can split it into the 2 terms with different geometrical interpretation. For calculations of these 2 terms, we will use the Dyer approach from the post-Newtonian expansions. In this approach, we split the space-time into 2 zones. The first zone is the near zone surrounding the world lines of the point particles, and the second one is the radiation zone, which is exterior of the near zone. Then, assuming that the observation point is far in the radiation zone, the retardation of scalar field inside the near zone is negligible, and the energy momentum density of scalar field is negligible, we can restrict the integration limits in 2 parts of the scalar field contribution into the gravitational field to the following regions in the near zone. And then we can also perform the multiple expansion of these terms to 2 integrals and calculate the spatial part of the integral of the near zone by the methods developed also in the post-Newtonian expansions using the equation of motion for the point particles. And as a result, we obtain the following expression for the first term in the scalar field contribution, which is divergent at the retarded moment of proper time. And we find that the second term is just the counter term for the first one. We just subtract the divergence from the first one, which is contained in the upper integration limit. Also, in accordance with the Rorley-Teitelbaum approach, we find the long-range part of the derivative of the gravitational field produced by scalar field, and it's found to have the following form. Combining it with the contribution of point particles, we arrive at the following form of the emitted part of the gravitational field produced by the binary, and it depends on the fourth derivative of the second mass moment of the system defined in a standard manner, and it also, again, depends on the entire history of motion of the binary preceding to the retarded moment of proper time. However, in the transverse traceless gauge, we can replace the second mass moment.
The time's up now, so could we just move over to summarize and conclude?
Yes, of course, to conclusions. So here are my conclusions. Despite the violation of the Huygens principle in odd dimensions, the gravitational radiation can be calculated by in standard matter by the integration of the energy momentum flux in the wave zone. Considering the gravitational radiation of the scalarly interacting non-relativistic binary on the free brane, we obtain the 5-dimensional analog of the famous quadruple formula, which in our case depends on the fourth derivative of the quadruple moment, and also depends on the entire history of the binary motion preceding to the retarded moment of proper time, which is a crucial difference from the 4-dimensional case. Also, we found that the generated gravitational waves have 5 polarizations, and that the brane leading observer would detect only 3 of them, also in the case of the circular motion of the binary, for example. And the third additional polarization will be predicted earlier, the breathing polarization. Considering the case of circular orbit of the binary, we found that only a half of generated gravitational wave energy is emitted into the free brane. And also we considered the quasi-circular orbital evolution of the binary and found that it differs significantly from the 4-dimensional theory. So this system was just the toy model. Of course, it's insufficient in comparison with 4-dimensional gravitational general relativity. However, it was very interesting toy model to consider the odd-dimensional gravitational waves in the presence of Huygens principle violation. Thank you for your attention. I will be happy to answer your questions if you have them.
Okay. So let's thank the speaker. Anybody like to ask any questions? If you've got a question, just unmute and ask. Okay, look, I don't see any questions, so let's thank the speaker again. This brings us to the end of the session. If anybody's got a question they'd like to ask one of the other speakers, or Mikhail, I think we can now put this open for general discussion. Any questions anybody would like to ask anybody? So if you've got a question, just please unmute and ask it. Or questions, comments, anything. Okay, I'm not seeing anybody. There's nothing in chat either. I'm not seeing any questions raised. So let me take this opportunity to thank everybody for their participation. Um, as I said, the organizers have informed me that recordings of these sessions will be made available after the conference and they'll be shared with all the participants. So thank you very much for coming, and thanks to all the speakers for their presentations. Good evening, everybody. Good night. Okay,
Thank
hi,
you.
Vanessa. Good night. Night.
Thank you.
Okay,
Bye.
good night. Good night, everybody. Okay. Okay, yeah, good night, everybody. And